Section 3.4. The Fundamental Theorem of Algebra. The fundamental theorem of algebra tells us if p is a polynomial of degree n, then p has exactly n linear factors. The polynomial can be rewritten as a product of its leading coefficient and all of those linear factors. Let's do an example. Let's find all the zeros of this polynomial and write the function as a product of its leading coefficient, 2, and its linear factors, whatever they are. To do this, we'll start with the rational root test to give us a list of possible rational zeros. We'll use synthetic division to see if they work, and if so, that will give us a reduced polynomial to work with. The rational root theorem is the p over q theorem. The rational root theorem tells us that for any root p over q, the p's have to divide the constant. That's -4 in this case. What are the factors of -4? Well, plus or minus 1 divides -4, plus or minus 2 divides -4, and plus or minus 4 divides -4. The rational root test tells us that the q's, the possible denominators, have to divide the leading coefficient. So in this case, that's 2. So what are the factors of 2? Plus or minus 1 and plus or minus 2. Since we're going to divide them with plus or minuses from the top, we don't need to write the plus or minuses for the q's. So if we make a list of possible p's over q's, we take each one of these and divide by each one of these. If you take each one of these and divide it by 1, nothing changes. Plus or minus 1, plus or minus 2, and plus or minus 4. If I take all of these and divide it by 2, I get plus or minus 1/2. 2 over 2 would be plus or minus 1, which we already have. And then 4 over 2 would be plus or minus 2, which we also already have. So this is an exhaustive list of the possible rational roots. Now that we have this list, we'll use synthetic division and the remainder theorem to test if these are roots. If we use synthetic division and get a remainder of 0, we'll know that it's a root. We'll start with -1. Put -1 here in its box, and then the coefficients of our polynomial, remembering to put any zeros if necessary. Here, 2 is the coefficient of x to the 4th, -1, -4, 10, and -4. We have every power of x less than or equal to 4, so we don't need to put any zeros. We draw a line, bring this 2 down, and multiply. 2 times -1 is -2, -1 plus -2 is -3. -3 times -1 is +3, -4 plus 3 is -1. -1 times -1 is +1, 10 plus 1 is 11. 11 times -1 is -11. -4 plus -11 is -15, which is not 0, so this is not a root. I can cross that off the list. Next, I'll move to +1. 2, -1, -4, 10, -4. I bring the 2 down. 2 times 1 is 2. -1 plus 2 is +1. 1 times 1 is 1. -4 plus 1 is -3. -3 times 1 is -3. 10 plus -3 is 7. 7 times 1 is 7. -4 plus 7 is 3, which isn't 0, so 1 is also not a root. Let's try the next one. -2. Again, 2, -1, -4, 10, and -4. I bring the 2 down. 2 times -2 is -4. -1 plus -4 is -5. -5 times -2 is +10. -4 plus +10 is 6. 6 times -2 is -12. 10 plus -12 is -2. -2 times -2 is +4. -4 plus +4 is 0. That means that -2 is a root of p. So far, now we know our original polynomial p of x factors into x minus -2, so that's x plus 2, times a polynomial given here, which is going to be 2x to the 3rd, which is 1 less than 4, minus 5x squared plus 6x minus 2. This polynomial here is called the depressed polynomial, which we get from here. We can use the rational root test again on this polynomial. This polynomial has constant -2, which means the possible p's no longer contain plus or minus 4, because 4 and -4 do not divide this. Everything else remains the same. So I can cross out this 4 and just check the remaining possible rational roots. Here, the next one is +2. So I put +2 in a box, and now I'll use the depressed polynomial. I'm going to use this one. I'm doing synthetic division on this to factor this. 2, -5, 6, -2. I bring the 2 down. 2 times 2 is 4. -5 plus 4 is -1. -1 times 2 is -2. 6 minus 2 is 4. 4 times 2 is 8. -2 plus 8 is +6. That's not 0. This one's no good. Next, we'll try a half. Again, 2, -5, 6, -2. We bring this down. 2 times a half is 1. -5 plus 1 is -4. -4 times a half is -2. 6 minus 2 is 4. 4 times a half is 2. -2 plus 2 is 0. This one's okay. Now we know that p of x is equal to x plus 2. The other root we found was -2. Then x minus 1/2, the new root we found. And then what's left over? 2x squared minus 4x plus 4. Once we get to only 3 terms, we've gotten to a quadratic. Now we can use all of the techniques we learned in Chapter 2. Step 0 is to factor out the greatest common factor. Notice that these 3 terms all have a 2 in common. So the first thing I'm going to do to make things simpler is to factor that 2 out. So p of x is x plus 2 times x minus 1/2 times 2 times 2 times x squared is 2x squared. 2 times -2x is -4x. And 2 times +2 is 4. I'm just factoring out a 2 from this term. This is equal to this. Now I'm going to factor this quadratic. Now, there aren't two numbers that multiply to 2 that add up to -2, so this isn't going to factor over the integers. We can't factor it that way. So instead, I'll find the zeros by using the quadratic formula. The quadratic formula tells me that this will equal 0 when x equals -b plus or minus the square root of b squared minus 4ac all over 2a, where a is 1, b is -2, and c is +2. So that means -b is -2, so that's +2, plus or minus the square root of b squared, that's -2 squared, minus 4, a is 1, c is 2, all over 2a, which is 2 times 1. That's 2 plus or minus the square root of -2 squared is +4 minus 8 all over 2. That's 2 plus or minus the square root of -4 over 2. The fundamental theorem of algebra applies over complex numbers, so that means I do have to worry about complex roots. In this case, we have the square root of -4. Square root of -4 is I times the square root of 4, which is 2 plus I times 2 over 2. That's the same as 2 over 2 plus or minus 2i over 2. The 2's will cancel here, and I'll get 1. The 2's will cancel here. I'll get plus or minus I. So now I know the zeros are -2, +1/2, 1 plus I, and 1 minus I. So I have found all the zeros of polynomial p of x. Now I'm going to write the function as a product of the leading coefficient and its linear factors. The fundamental theorem of algebra tells us that when you find all of the zeros, you can rewrite the polynomial as whatever the leading coefficient is, a, followed by x minus each root. So p of x is then a of the original polynomial, which was 2, times x minus -2 times x minus 1/2 times x minus 1 plus I, and then x minus 1 minus I. Now I've written all of the zeros of p of x, and I've written p of x as its leading term and all of its linear factors.